Hello, good morning, good afternoon, good evening, wherever you are. My name is Thomas Kirk, and I'll be hosting today's webinar on accelerating MMC V-cycle development. At this moment, you should be able to see my screen. So today's presenters will be myself, your host. We'll also have two very exciting keynote speakers. So the first one will be Sébastien Sylvain from the Supergrid Institute in France, and followed by one of our own, Weiwa Wang, the Chief Representative of the Technical Center in the Asia Pacific. The outline will be as follows, so a brief introduction followed by a description of MMC V-cycle development, followed by Sébastien and Weiwa's presentations, and a question period. So MMC has proven to be an efficient and flexible alternative to traditional voltage source converters with several benefits, including low harmonic distortion, a compact footprint. So we've seen this technology grow within not just the research, but also in infrastructure projects. So we've adapted our product line as a result to better suit the needs of this industry to help accelerate projects and to bring not just tools, but methodologies that could help this type of development. So beginning in 2010, there was the Transbay project in San Francisco, which we didn't participate in, but it motivated us to get into this area. So rather quickly, we started in China in 2011 in Nan'ao with a small project, but over the years, we've had a lot more influence out there. And Weiwa will talk to you more about what is going on in China. But we've also had, and I should note, these are all real MMC infrastructure projects. We've had also RTE's use of our equipment in Spain and France, so there's a HVDC link that crosses between these two borders. And then in terms of research, well, in China there's been some of our clients that have been performing research for a while, but we've found now that not just in Asia, but in Europe and North America, there's a lot more interest in MMC. So we really see this becoming more of a global phenomenon in terms of how the technology will be used. And our aim is to supply the world with testing equipment for that. So what does MMC offer? What is the nature of it? Well, it's cellular, so you have these cascaded cells, and I mean, in industrial MMCs, you might have thousands. So generally, the cells themselves are cheaper, and the converters could be quite expensive. However, due to the low PWM carrier frequency used to control these cells, you actually end up with less power electronic losses at higher powers than conventional VSCs. Also, because of the harmonic cancellation due to the cells, you don't need AC filters, and because you have so many cells, you can function with out-of-order submodules. So those are some of the main benefits. I mentioned also that it's more compact than the classic HVDC. And although currently the primary application in infrastructure is for HVDC power transmission, there's also some projects that have looked at asynchronous power system coupling and renewable energy integration, which Weiwa will talk to you about later. And of course, you can use this technology as a StatCom. There's also potential in using them in DC distribution networks, so for example microgrids, DC microgrids, and for high voltage motor drives. And surely there are more, but for today, we'll stop there. So when you look at the projects, the real infrastructure projects out there, all of them use half-bridge submodules. The disadvantage of these submodules is that they can't clear DC faults effectively, so these projects are forced to use underground lines, and they have to limit their power range, so sub 1,000 MVA. However, the future, and currently you have companies looking into solutions that involve DC breakers with or without current limit resistors, and you have researchers out there investigating other topologies and configurations. So for example, you could have a mix of topologies within one converter. When you look into this, you'll see that there are trade-offs. So no technology is perfect, and in fact, not every product is mature. MMC is a relatively new technology. It only started in the mid-2000s, the concept. And in fact, when we look at power electronics, some of the technology in that area still needs to catch up to the ideas in MMC. So, but generally, whether you have an idea or a product, you'll want to study or test it prior to deploying it. This is easier said than done. So if we look at the typical structure of a MMC system, so you'll see here we have MMC valves, which are controlled by their own controller, which receives voltage reference signals from a PCP. So this is a pull controller. And then that will take its readings from the substation, shall we call it. So to recreate this setup in a laboratory in a simulation is actually quite a bit of a challenge. So number one, if you want to perform a desktop simulation, this can be inefficient due to primarily the number of valves, the number of switches that must be simulated. But it doesn't also account for synchronization or latency, either within a controller itself or between controllers, between systems. So there's also the element of protection, not to mention there could be some rather large distances between terminals. And also, if you wanted to build a test bench, so shall we call it a mock-up, this can be very lengthy. You'll have to manufacture the entire test bench. You'll have to test it itself, validate it. So this is a very useful tool because as long as it's safe and actually performs the job that you want it to. So we're going to stop briefly for 20 seconds or so for the first poll. You should see it pop up onto your screen. So the question is, towards which areas and applications do you see MMC technology going? When you click, that's your answer. And then after 20 seconds, we will continue. So we can see the results, and at least half of you are still see this area staying in HVDC. 20% in microgrid, and 11% medium voltage drive, 8% power transmission islands. So we'll continue. I'll talk now about what the V cycle is. So just a brief background. This technique, this process, which actually, as far as I could find, started in Germany in 1986, was actually initially conceived for planning and executing projects by the German government. In this case, an implementation, and then you have the right side of the V, which is the integration testing. And the idea is you're going to follow that V to actually accomplish your project, to finish your project. However, you should note, if you do research on this, you're going to find a lot of variation. You're going to find variation due to the different sectors that employ this. For example, software versus product design is very different. But we'll focus on history. So one example that really we believe is analogous to MMC is electronic control development. So ECUs are computers that are used in cars to control motors and other systems. So in that industry, you would start off with a desktop simulation where you would model your plant as well as your controller. And then you would proceed to perform what is called rapid control prototyping, where you can prototype a system on a simulator and connect it to a real plant. So that plant could be, for example, an electric motor connected to a dyno. And then based on your prototype code, you would actually generate real code and load it onto a real ECU, and you could test that ECU on a real-time simulator, which would not just necessarily model the electric motor, but could also model the transmission, the suspension, whatever you can fit into that platform. And then finally, of course, when you actually validate the real controller, you do it on the real motor, you would do it with the real vehicle eventually, and then you would sell your car. So when we look at that and we compare it to MMC, well, MMC is such a control-intensive domain that we could really apply it towards this industry. So I'll go over the different stages, and for the most part, we can help with these two and the HIL area. Of course, validation manufacturing, we can also assist in that, but that's more up to the final product, the final design. So let's look at desktop simulation. I mentioned earlier that simulating a large number of submodules can be very time-consuming, and so that will actually force certain users to actually use MMC average models. So you sacrifice detail, or maybe you actually use fewer cells in your simulation, but the reality is that you lose some fidelity, and manufacturers, R&D organizations, and also the future owners of these MMC systems, which are very expensive, would rather perform detailed simulations. So how do we leverage parallel computation and FPGAs? I'll talk a little more about that later, but the truth is we ran a study on it comparing desktop simulation to parallel simulation, to FPGA-based simulation, and you'll see here that the red and the blue is the baseline. So this is real-time CPU simulation, FPGA-based simulation on one of our systems. And in the purple, this is a conventional desktop simulation. And green, this is actually an optimized desktop simulation that we've performed with our software. So just for 48 submodules, which when you look at an industrial MMC project is very little, we are 1,000 times faster when we use a real-time computer or FPGA. So imagine if you were to look at a system with thousands of submodules. In some cases, you wouldn't necessarily be able to simulate that system. Rapid control prototyping. So as I mentioned, RCP could be a very valuable tool for MMC. Why? MMC control strategies are complex, they're multi-layered. So gaining efficiency in this stage is a boon. So how do you do RCP? Well, RCP involves using a system such as a real-time computer to rapidly prototype your controller. But how do you test that prototype? Well, you can use either a real-time simulator to perform hardware in the loop, or you could use a physical test bench. So the reason for using a physical test bench is that, number one, it's going to have much more realism relative to the real-time simulator in the sense that it'll be the real thing. It'll capture nonlinear behavior, sensor noise, measurement latency. Why you wouldn't use it necessarily during the HIL testing phase I'll describe later, but it'll become pretty obvious. So one of our users actually joked to us and they said, I think this is after they spent like 1 or 2 years making a bench. They said, why don't you make benches? So we started making them. And that's what I'd just like to talk briefly about is the OP-1200 or 1200. So this is an MMC test bench. It's a turnkey solution, so it's delivered with hardware and software, including control algorithms for HVDC. And this is something that can be used not only for research, but for a student laboratory in undergrad, for example. So you'll see there's a real-time simulator in this rack, which is effectively the controller. And then we have these 6 boxes which actually contain 10 submodules each, which can be configured in half-bridge or full-bridge configuration, and each one is actually a MOSFET H-bridge. So this is effectively the schematic that represents that. The system also comes with a protection box, so emergency stops, safety features, and so on, a measurement box, and an inductor box, which you need obviously to complete your MMC circuit. Now, the simulator actually communicates with these cells via fiber optic, and the standard configuration, so one rack is rated for 6 kilowatts, 400 volts with the full bridge configuration, and you would have 11 levels per arm, so 60 submodules in total. What's interesting about this setup is even though it comes delivered with a control algorithm already packaged, you can actually use RTXSG, which is a way of modifying firmware to create custom controllers. So this is very exciting if you're doing research on new control algorithms. A little more about the bench. Well, even though it's primarily targeted at the moment for HVDC, it could be configured as a scaled-down model of other systems. So, for example, you could look at AACs or FACS, STATCOM, as I mentioned earlier. Solid-state transformers could be potentially configured in this, and it could be used as a power amplifier. It comes prepackaged with control algorithms, documentation. So that's what it's made for, is student labs, if it isn't modified. And you can combine it. So by combining, I mean you could have more than one rack to actually add more submodule levels, or to increase your, and to increase your power. But you could also link multiple racks to perform back-to-back converter or multi-terminal studies. And something I won't touch very in much detail, you could use this setup with power hardware in the loop with other real-time simulators to study converter grid interactions. So, I mean, we will share this presentation. So afterwards, take 10-15 minutes to check out the video that we've made with Jerome, who's the lead designer of this bench, and he's going to show you all the features. It's really a nice video to explain how this works. And of course, you can always contact us directly if you want us to show a demo or whatever. We look forward to hearing you about this. The last part of the V that we support is hardware in the loop. So there are a couple challenges in performing HIL. The first one is simulating a large number of submodules fast enough. The second one is interfacing with real valve and pole controllers. So you need fiber optic, analog and digital connections. So just to give you a benchmark, currently a CPU can simulate around 600 submodules directly on the CPU. This is one of our systems, by the way, at a time step of 50 microseconds, so 20 kilohertz frequency. As of today, a Vertex 7 FPGA can simulate up to 6,000 submodules at a time step of 250 nanoseconds. So that's a 4 megahertz frequency, and not only in one topology, in 3 topologies. So this is a huge performance gain by using the FPGA. And finally, we've integrated SFP support not just with Aurora or Gigabit Ethernet. We can actually create custom protocols using RTXSG, the custom firmware development platform we have. So when you have a controller, a valve controller that needs to control thousands of valves in the field, the idea of using the FPGA becomes very valuable. So as I mentioned earlier, you might gain certain realism by using a test bench, but that test bench only has 11 levels per arm, or maybe 30, 40 levels per arm. So this is why we propose, and actually why many of our users use FPGA simulation for this stage of testing. And one of the really interesting things, so as I learned more about these projects by working at OPAL-RT, we actually find that our customers are really interested in detailed power system models that are linked to their MMC simulation. So you'll actually not only find clients of ours that will use one box, they'll use multiple boxes to really represent a multi-terminal system connected to a power system that's modeled on a simulator. So you can actually end up with a simulation that has a lot of detail. It's not just a question of testing one converter on an FPGA. So at that, I'm done for my part. We'll end with a quick poll. And the question is, how would you use an MMC test bench in your laboratory? So say you were given one tomorrow, how would you use it? So we have 60%, let's say, for MMC control development and research, 20% for new topology research, and 13% for teaching laboratory. So on to our keynote speakers. I'll introduce Sébastien Sylvain very quickly. So he has a very impressive resume, to say the least. He has almost 10 years of experience in research and technology in the areas of electrical products and scientific software development, so mostly with GE Energy Connections grid solutions. After leading innovative projects of new high-voltage circuit breakers, managing teams developing and deploying numerical simulation suites, Sébastien is now responsible of an R&D group at Supergrid Institute, with the objective of developing models and applying real-time simulation for the study of the architecture, the control, and protection of HVDC grids. So without further ado, it's my pleasure to introduce Sébastien.
Hello everybody. So my name is Sébastien Sylvain and I work for Supergrid Institute. I would like to thank OPAL-RT for giving me the opportunity to share our experiences with OPAL-RT systems with a focus on modular multi-level converters. After a first part describing what is Supergrid Institute and what are its research fields, we will go more into details about Supergrid's real-time simulation platform and its use for the acceleration of the developments involving modular multi-level converters. About the context, so what is a supergrid? A supergrid is a wide area transmission network that makes it possible to trade high volumes of electricity across great distances, up to several thousand kilometers. There are many reasons to believe that such interconnected electricity highways will be based on HVDC technology. It is a promising solution bringing high flexibility in the power flow patterns, but there are still technical barriers for the creation of meshed interconnection that have to be addressed. What are the advantages of supergrids? Such large-scale grids allow the smoothing of the intermittent generation profiles of the renewable energies by interconnecting them. And at the same time, it brings a time offset in the consumption peaks, which is also a smoothing effect. The vision for the pan-European network encompasses the connection of major reserves or renewable energy such as the northern offshore wind fields and the southern solar fields. Now about my company itself. Supergrid is what we call an Institute for Energy Transition, created within the framework of the French government's initiative called Investissement d'Avenir. There are around 10 ITs in France. ITs provide platform for interdisciplinary research in the field of low-carbon energy. They bring together the expertise of the industry and public research in a logic of co-investment. They stimulate the collaboration between those different actors. So the mission of Supergrid is to perform collaborative research activities, and the goal is to lead to industrial and commercial application. More concretely, the objectives are to develop new technologies for the construction of supergrids, to generate intellectual property rights with patent applications, for example, to federate the French industry around supergrid challenges, and to develop education programs. So we have already learned that Supergrid is a collaborative research center. It involves private industry and public laboratories. It owns equipment for simulation and testing. Its research staff, around 150 employees, is mostly provided by its partners, actually its shareholders, and is gathered in one location. The research activities of Supergrid are organized around 5 research programs. The program 1, to which I belong, is about the Supergrid architecture, operation and control. This is a program with a system view, whereas the other programs are working on primary components of the networks. The program 2 develops technologies for current breaking, isolation and measurements. Program 3 focuses on power conversion technologies, and the 4th one on HVDC cables and lines. The program 5 studies the resources for stabilization of the network and energy storage, and is for the time being mainly working on variable speed pump storage plants. Okay. Supergrid is situated in the city of Villeurbanne, close to Lyon, and has some facilities, even if some of its main technical platforms are already deployed. Its offices and most of the test facilities are still under construction, with an opening scheduled this year. In particular, there will be a platform for ultra-high voltage tests associated with a very high power generator. Now about the real-time simulation platform. So there will be 200 square meters, mainly based on OPAL-RT systems. The software we use are for offline simulation, EMT-PRV and MATLAB SimPower system. For real-time simulation, HyperSim and eMegaSim. We also have some solutions for FPGA-based co-simulation with the MMC run for 512 levels MMC converters, the generic electrical solver called EHS. We have also some drivers for using the IEC 61580 communication protocols. And concerning the hardware, we have several real-time targets with complete input-output capabilities, lab-scale MMC test bench, some power amplifiers, and measurement reducers. So this facility is available for partners and customers. We can perform concurrent engineering, relay testing, MMC control replica testing, to name a few. Okay, so what are the drivers for the real-time simulation of HVDC grid? Here we can see a sketch of 3 terminals HVDC grid composed of interconnected MMC converters. Our study addressed the problematic of MTDC grid protection and control, and for those studies to be accurate, it is key that the MMC models and controls and the DC overhead lines and cable models are accurate. For the rest of the presentation, we'll focus on the topic of MMC models and controls. So first, a little theory. So let us talk about the structure of the MMC control algorithms. The development of control strategy of MTDC grid starts with the development of a good control of the MMC itself. Here we can see about, one possible architecture of an MMC control, which consists in a cascaded control loops. The high-level control receives references of DC voltage, active or reactive AC power, etc. And the converter also has storage capacity with its capacitors and can play a buffer role. Therefore, its internal energy also has to be managed. Oops, sorry. The outer loop satisfies those demands by generating arms currents to the inner loops, which in their turn create arm voltage reference to what we call the low-level control. The low-level control manages the state of charge of the submodules by carefully selecting the right submodules to insert or to remove to realize the desired voltages. We will see how such control architecture is prototyped on OPAL-RT systems. The converter is not always under control, especially when half-bridge MMC is submitted to a fault. Now what happens when there is a fault? Under a fault, the MMC capacitors, the current will rapidly increase because the capacitors modules start to discharge into the fault. The MMC will stop the discharge of the capacitor into the fault by blocking the IGBTs, and then will auto-protect its IGBTs, more precisely its freewheeling diodes, by switching on parallel thyristor, which will bypass the submodules. And finally, the entire converter will behave like a diode bridge. All that to say that for the creation and validation of protection strategy for MTDC grid, it is mandatory that the behavior of the MMC under fault is properly modeled and simulated. Now let me show a few examples of the setups based on OPAL-RT system that we use. Here is one of the first setup we implemented. So it's based on the MMC test bench that we can see on the top. The MMC control are embedded on a OP-4500 real-time simulator, and the MMC is connected to, on its both sides, to sources, one AC voltage source and one DC current source that emulates the DC grid. So it's what we call a rapid control prototyping setup. Now we can see a few experimental results using this setup. It's an AC reactive power step change that occurs at 0.1 second. So we can see that the AC power is going from 0.4 to PU to minus 0.4 PU. And we can see the effects of this power step change on the average capacitor voltages of the different arms. And we can see also the effect on the AC current, which a sudden change on the phase at the time of the step change. Okay, another possibility is to use this test bench in a power hardware in the loop setup. So power hardware in the loop simulation is the integrated simulation of a complete system with one part simulated numerically and the other part using the real converter. So from the MTDC grid perspective, it adds the complexity of the real converter. And from the MMC perspective, it adds the complexity of the real environment and not only ideal sources. So for this, we will use the OP-5700 real-time simulator to simulate the grid, and we will interface the MMC test bench with this real-time simulator using power amplifiers. The last setup that I will describe is a mix between hardware in the loop and rapid control prototyping. The control will be embedded will be prototyped, and it will be connected to a real-time simulator. So that's why we call this hybrid HIL and RCP. For the MMC control algorithms, we use MATLAB Simulink for this, their implementation, and they are then executed in real time using RTLab. The high bandwidth necessary for the input-outputs and the intensive computation of the low-level control requires the use of FPGA. Its bit streams are created using the RT-XSG toolbox, and we see that those two components of the control are embedded on the OP-4500. This OP-4500 is then connected through optical fibers to a second real-time target, the OP-5700, which will then execute the real-time simulation of the power grid using HyperSim. The detailed simulation of a full-scale MMC with time steps of hundreds of nanoseconds requires the use of an FPGA, which bit stream is also programmed using RT-XSG. This HIL setup also allows the connection of full-size control replicas, replacing the OP-4510 by real control cubicles. So in conclusion, the use of the MMC real-time simulation systems and the MMC test benches allow to perform feasibility studies and to develop new concepts. We were able to design and test MMC controllers and to validate the MMC models for a wide variety of applications. Those systems enable higher technological readiness levels for the MTDC protection strategies that we develop, and also for the MTDC control algorithms and mode management that we develop. We believe that we can reach a level 5 of this technological readiness level scale for our developed strategies. So thank you for your attention.
Thank you, Sébastien. It's a very amazing project. So we'll continue soon with Weibo, but before that, here's the third poll of the wherever you are. So the question is, what is the most important feature when performing MMC HIL testing? And while you're doing that poll, I'd just like to remind you that you can always ask questions through the interface. We'll be taking questions at the end. It's a chat question interface. So please feel free to send any question you have for either myself, Sebastien, or Weiwa. And once you exit the webinar afterwards, you will also be asked an exit poll basically to get your opinion on the webinar. So don't forget to do that when you leave. So based on this poll, we see a 58% fault simulation result, split evenly at around 12 to 15% for the second to fourth categories. So up next, we have Weiwa Wang. So Weiwa is the Chief Representative of the Asia Pacific Technical Center of OPAL-RT Technologies. He received his Master's in Science and Electrical Engineering degree from the University of New Brunswick in Canada in 2007. He specializes in the simulation modeling for electromagnetic transient EMT studies with focus on VSC-based HVDC systems, DC distribution networks, and smart grids, as well as a complex medium voltage drives. His career started as a specialist in real-time simulation and hardware-in-the-loop testing at a Chinese integrator for OPAL-RT in 2007, and he actually then joined OPAL-RT in 2009. He has been involved in the commissioning of one of the largest real-time simulators with more than 3,000 input and output channels. This project started in 2011. He's also led the implementation of hardware-in-the-loop test benches for the Nan'ao and Xiamen multi-terminal MMC HVDC projects. So without further ado, here is Weiwa.
Hello, everybody. So this is Weiwa. In the past 5 years, there has been 5 MMC HVDC projects commissioned in China, while 3 another project are on the blueprint. So those are the yellow star are the 5 MMC projects that has been already commissioned in China, and those red circle are those currently on the blueprint. When I look back, I'm very proud of seeing my footprint in all the labs where the controlled protection system were studied and tested for those projects. So today I would like to share 2 user cases that show how the real-time simulation can facilitate the test in the V-mode development cycle of recent MMC projects in China. The first case is about the Nan'ao project. Nan'ao project is the first multi-terminal MMC HVDC system in the world. So this plus minus 160 kV, 200 megawatt MMC HVDC transmission system was built to collect the wind power from the island to the mainland, and also offer a possibility to execute black startup of those wind turbines without adjacent AC power supply on the island. The challenge of this project not only came from the complexity of the control and protection system itself, but also the coordination among all those 25 cabinets manufactured by different suppliers. To overcome those challenges, the EPRI of China Southern Grid led the R&D integration test and commissioning following this V-cycle, although it might not be named V-cycle at that time. At first, they used the accelerated software in the loop to validate the defined strategies and specification. Then the manufacturer would develop their system following specification from the CSG. Before implementing the production code, some of the manufacturers test the prototype on their own homemade test bench, while others perform the unitary test on an HL platform. Before the field commissioning, CSG put together all the controller and protection systems from different manufacturers and conduct integration tests on a hardware-in-the-loop test bench. OPAL-RT real-time simulator was built to test the static and dynamic performance of the control system. The test used detailed MMC models that contains 3 times 1,200 sub-modules. and the valve controller is directly connected to the simulator by fast serial protocol. The time step of the MMC valve was 250 nanoseconds, or the sampling time was 4 megahertz, which is very fast. And we used 25 microseconds to simulate the wind plant and the power grid around the MMC HVDC system. There were 561 scenarios that have been tested repetitively on the HIL system. So at the end of the V cycle, the HIL model has been fully validated at all the different stages. So it becomes a very valuable asset for the maintenance, because the utility or the owner of the MMC HVDC can connect a replica of the controller to validate on the validated HL test bench, on which they can reproduce an accident from the operation. And they can also optimize the protection algorithm based on the incident. So as a conclusion, the V-cycle-based implementation can significantly increase the efficiency of design and test in this MMC HVDC project. We can see that the commissioning went very well. It took only 3 months. And after that, the now MMC HVDC system has been stably operated since 2014. Only in the year of 2015, 400 billion kilowatt hour wind power has been integrated via the multi-terminal HVDC system. The second case is the Xiamen MMC project, which is the first bipole MMC HVDC link rated at plus minus 320 kV and 1,000 megawatt to supply the power to the downtown of Xiamen. Besides those similar challenges to those in Nan'ao project, Xiamen project was facing another challenge that organized the test, because the controller in each terminal consists of the parts supplied by 2 different manufacturers. Each manufacturer has its own development cycle. Although the integrator tried to synchronize the both manufacturers very hard, but there was still a small delay between the 2 cycles. How do we test the controller if only part of the system is ready? A solution was found by using a combined hardware in the loop and software in the loop test bench. In this case, the pole controller and the circulating current controller were the production equipment to be delivered to the field. They are connected to the simulator as in a standard hardware in the loop test bench. Although the physical voltage balancing control was not available, the production code implemented on a similar FPGA can be used on the FPGA that was used to simulate the MMC valve. So the simulated VBC acquired the adapted voltage reference signal from the physical controller using the same HDLC protocol used in the field. So when it comes to the last page of my presentation, the test result of deblocking at the sending end of the MMC valve is compared to the actual field testing result for the same scenario. So we can see that waveform for both voltage and at the AC side and the current at the AC side and the DC voltage are quite similar. It proves the HIL and the software in the loop platform is quite a feasible solution, particularly when only part of the controller is ready. So this is pretty much all the cases, but I hope you can ask some questions if you want.
Thank you, Weiwa. So before we go to the question period, and of course, let me remind you that through the interface you can ask questions. Please type them in, send them off. So we're here waiting. Before we actually go to that, I just want to make sure that you know that you can contact all of us via email or phone. I'm sure you take some time to come up with ideas, questions. We're very open to speaking with you. And yeah, you can, so before the questions, I should add, we're actually going to have a regional user seminar in Atlanta, so that's coming up very soon. We have already quite a few registrants. We've changed our website a bit, so the Resource Center, where you can find technical presentations, other presentations, videos, manuals, whatever it may be, you can find that all on our new website in the Resource Center. And as I mentioned earlier, you can go see this video that we made to show in much more detail the OP-1200 MMC test bench. I'd like to thank Sébastien for his time, Weiwa as well. We had a nice audience today, so thank you very much for coming and spending an hour with us, and we look forward to hearing from you.